So last time we started to do analysis of trusses, and as I said, analysis software for any software, not only structural engineering, garbage in, garbage out. I worked with hydrologic softwares. It's all about data. The way that you model the data and the way that you understand the software is going to give you results. So don't accept the result as is. Like as is, like you need to look into the results that you are going to get. Is it reasonable or not reasonable? Like the way that we did the structure analysis last time for a truss, and there's bending moments. So definitely there's something wrong. And we start to hit mistake by mistake until we finally figured out how we do structure analysis for trusses. Also, one thing that I needed to mention, do you guys remember when we started to do partial fixity last time? So partial fixity, actually, it's a very interesting tool. Just want to mention something before I start the new application so that you can understand how to use the full function of partial fixity. So I'm going to open the example from last time, and I'm going to unlock the model. And then I'm going to select one member, and I'm going to say assign frame partial fixity. Okay. So right, for partial fixity, if you have a truss, if you have a frame member, okay, as we said, the SAP 2000 only have frame member to model any 1D problems, either trusses, frames, beams, it's all called a frame member. But the way that you put in the condition on this frame member, the analysis on SAP 2000 is going to perform in a different way. Like if you said that there is no any load in between here, like you didn't put any on wave or any concentrated loads, and you said that the moment here is 0 and the moment here is 0, so that's just going to be a truss member. But if you guys remember in the first lecture when we draw like something like this, fixed, and then we said that this has a distributed load, something like W ton per meter, right? Do you guys remember this? And then we tried a few different things. We put a spring here, right? So if I model this structure without spring, what I'm gonna do, I'm gonna select this member and assign partial fixity to this member, but not at the start and the end. Just at the end, not at the start. Do you guys understand that? So modeling intermediate hinge, I need to look out, like for truss, something like this. Every point on this truss is an intermediate hinge. Every point has moment equal to 0. There's no moment here or here. So that's why we applied end to end, start to end, end. But there is moment because this is fixed, but this is intermediate hinge. So the moment here is 0. But let's say that we have a rotational spring K is equal 200 ton meter per meter. Okay, that's a rotational spring. The rotational spring K is equal to, that's how I figure out if my unit is true or not. So K is going to be equal M over delta, right? Not delta, theta. So this unit is not right. So it's going to be radian. Because I know this unit is ton meter and this is radian. Okay. All right. So if you have, this is the stiffness of this rotational spring is 200. So the partial fixity here is not 0. You have to put the stiffness of this spring. And once you draw the bending moment here, it's going to be something like this. Here the moment is going to be negative. Let's draw the negative down. So here is going to be positive and here is going to be negative. And here the moment is going to be negative as well. If this intermediate hinge and there is no rotational spring, so the moment is definitely going to go to 0 and the moment here is going to go to 0 like this. But if you have a rotational spring here, there should be a little bit of moment here, something like this. The more the stiffness is going to be of this spring bigger, the moment is gonna make like this until you put this stiffness number that is really huge, like infinity, so the bending moment is gonna reach its maximum. Maybe you can try it. I believe, yeah, I can't remember. In 2015, I was teaching the stiffness method. And in one of the quizzes, and I believe I also did it in the lecture, I give an example how to solve this using the stiffness method. Like you have a spring and you have everything, and this moment, and you can actually solve it numerically, and we can solve it in SAP 2000. Maybe when we do the stiffness, and you have this problem using the stiffness method, you can do it on SAP 2000 as well, so that you can compare the results. So what I want to say is, like if I have this, I have to select this member, and then I say that the moment M is 3 at the start is not 0, so I don't check this. But here at the end, I need to release. So once you check this, so you are releasing the moment at the end, and then it's gonna put 0 and 0 here. If there's a rotational spring with a stiffness, you put the stiffness at the end, how much is it? Okay, so that's what I want to say. But also be careful. If you draw the member from here to here, that means here's the start and here's the end. But if you draw the member from here to here, this is the start and this is the end. So it depends on how you draw the structural member, okay? So let's, I have an application for that. So we have today this frame. It has, I believe it's a very good application because it has dead load and live load. It has different members, it has different sections. You have columns that are 25 by 100 centimeter, beams that are 25 by 150. You have a link member here or a tie. We call a truss member a link member. This is, we call it a truss member or a link member or a tie if it doesn't have any loads between the two hinges, and it has intermediate hinge at first and intermediate hinge at the end. So that means this member only have normal force, doesn't have bending moment, doesn't have shear force. That's from looking to this structure. Why? Because I have this intermediate hinge and intermediate hinge, so the moment 0 and 0, and there's no load in between. But if you put load in the middle, this is not a tie anymore. It's gonna have bending moment. Also, it's gonna have a bending moment because of its own weight. But if we neglected its own weight with respect to the total load on the structure, it's gonna be a tie, right? Okay, so right now, when I model this system, I'm gonna model every beam and everything. If I give you this problem in the exam to solve it for structure analysis, you are not gonna assume the own weight of the structure, right? You are gonna use this load to develop the bending moment. Because I didn't give you the gum of the concrete and I didn't give you anything. So, but I'm giving you these cross sections just to model the stiffness of the structure. So what I'm gonna do, I'm gonna neglect the own weight because I didn't tell you to consider the own weight, and you are gonna only consider the weights that I give to you, the live load and the dead load. Okay. So do you guys remember first time like last time when we said, if I'm gonna start doing a new model in SAP 2000, where should I start? I start first by file, new model, and then maybe I'm not gonna save this. And then first I check the units. I have my units, I go to my AutoCAD file, and I have all of them meter and ton, so I'm gonna keep this ton meter. And then we said that grids is good, is gonna help me to draw the structure, so I'm gonna say grid only. Okay, what is the number of grids in the X direction? I mean, like the minimum number of grids that is gonna help me to draw this structure. 3. 1, 2, 3. You can do 2, like you can do 2, but once you draw the structure, you'll find, oh, I have a cantilever here, so I need another grid. You can add it up, but it's better that you decide how many grids that you need from birth. Okay, how many grids in the Z direction? It's a little bit tricky. 1, 2, 3, 4, 5. Okay, so it's a little bit tricky. You can do 4, but in the middle you'll figure out, oh, I need an extra one. Okay. All right, so you guys tell me, actually, X is easy. X, you have 18 and then you have 3. But Last time, actually, when we did the truss, the spacing was like equal. Right now, it's not equal. So we need to figure out how we do this. The spacing in Z direction, we have 3, and then we have 6, and then we have 8, and then we have 6 plus 3, 9. Okay. So what I'm gonna do, I'm gonna say that I have 3 grids in X direction, 5 grids in Y direction, and then we figure the spacing in a different way. Okay, I'm gonna say 3 in X, 1 in Y, 5 in Z, and I'm gonna keep these spacing. Okay. So right now, I'm gonna check the X, Z direction. This is not actually what I'm looking for, right? So I need to change these spacing. So what I'm gonna do, I'm gonna do a right click on the screen, and there's something called edit grid data. So when I do the edit grid data, there's something is called modify the system, the grid system. Okay, so right now I can see all the grid spacing. Okay, I have 0, 18, and let's find out what is the other one. It was 3, so it's gonna be 3 plus 18 is gonna be 21. So what I'm gonna do, I'm gonna say there was 18, and then the next one was 21. And then in the Y direction, I don't have, but in the Z direction, I have 3, 6, 8, 9. Okay, so let me go back. 0, 3, 6, 8, 9. All right. And then I'm gonna say okay, and I'm gonna click on XZ. So that's the grid system that I have for now. All right. So right now the grid system is ready to draw the frame structure. Okay, so before I draw the frame structure, we agreed last time that we need to define the materials and cross sections first before I start the drawing. So I'm gonna go to define, and then materials, and then I'm gonna go check, modify this material. I'm gonna make it the same concrete unless in the project that I give to you or in the problem, it's a different material. I'm gonna give you the density of the concrete, the Young's modulus, or the compressive strength of the concrete, whatever characteristics that I'm gonna give to you, you are gonna input these characteristics here. So I'm gonna use concrete because I can see that my beams are concrete and they have a concrete cross sections. All of them are rectangle. So I'm gonna keep the concrete material here. I'm gonna say okay. Then I'm gonna go to define sections, and we have frame sections. I don't have any predefined frame sections like last time because I didn't start drawing. But if I start drawing, the software is gonna develop its own sections. So what I'm gonna do, I'm gonna add new property, and then I'm gonna pick concrete rectangle, and let's start with column C1 25 by 100 centimeter. So I'm gonna say C1 25 by 100 centimeter. And the units here are in meters, so the depth is 1, and here is 2.5. And I make sure that my material is concrete, not the steel one. And I'm gonna say okay. Okay, define the first section. Next section, maybe I can add new property, or I can add a copy of this property and just change the name. So I can change the name to column maybe beam 1, B1. It was 25 by 150 centimeter. This one. And is gonna be 1.5. And here 0.25. And then I'm gonna say okay. I don't have any other, oh, I have tie. This tie is 25 by 150. So let's add a copy of this property. And we just change the name to tie. What is the dimensions again? 2550. Okay, so I have everything's ready, and I'm gonna say, okay, so right now I define the section. For drawing, you can go to the draw tab here, or you can actually use the one that we have here. Okay, so I can use this one, but it's a little bit tricky. So I'm gonna go check this. This is from 0 to 8, and this is from 0 to 6, okay? So I'm gonna draw column 1 first, and I know it's from 0. Oh, I think we miss something. I did 3, 6, 8, 9. There should be like something here. Okay, let me double. Yeah. Okay, let's check. So I have 0, 3, 6. Oh yeah, that should be 9. Okay. So right now we see what is makes sense and doesn't make sense so that we can find out the mistakes. Okay, so did I change it? Okay, modify again. Still 12. 9. All right, here we go. All right, next step, I'm gonna do the columns. The columns are from here to here. So that's the 8. Right now, I can continue drawing, but the thing is I wanna draw another column here. If you wanna get out of this, you can make a right click. You are still in the drawing and you can still draw the other column. If you wanna get out, you make a right click and then you can change the cross section. So right now I'm gonna change the cross section to beam 1 and I'm gonna draw a beam 1 from here to here, and then I have a cantilever here, and then I'm gonna make a right click so that I can keep this activated, and then go draw the tie, and I have a tie from here to here, and then I'm done with the drawing. So I draw all the geometry that I have, except that I have to do the restraints. So the restraints that I have for these problems or the boundary conditions, I have 2 hinges here, which is very easy. I can select these 2 joints together, either up, down, or down, up. Okay. Actually, yeah, they are selected. You can do the selection that way, or you can do it that way. Doesn't matter. And I'm gonna click assign, joint, restraint, and then I'm gonna make hinge. Then I'm gonna say, okay. All right, so the hinges are modeled. So what else do we miss? The internal, you mean the intermediate hinges, right? So for this one, if I left it that way, that means this connection is rigid with the column. So this connection is going to transfer moment to the tie. But I have intermediate hinges here. Can you see these circles? So to do this, we are going to go to the assign, frame, and then release. And then I'm going to release the moment M33. M33, that means the moment that way. Okay, that's what we are interested at. The moment that is going to bend this that way. M22 is going to bend that way. We don't have any bending that way because the load is not this way. The load is this way. Okay, and all of them are 0. Okay, and then I'm going to say, okay, so right now we are done with the geometry modeling. Let's go to the load modeling. So we said to assign loads, we need to define load pattern first. SAP 2000 already have dead load defined. So I'm going to change this to 0 because we don't have any self-weight in this problem. In real life, we have, but not in this application. And I'm going to name the second load pattern live load. And I'm going to change the type to live. I'm going to add new load pattern. Okay. And then I'm going to assign the load. So let's check what loads that we have. This beam has 1 ton per meter horizontally projected. Okay, be careful. Horizontally projected. What does it mean? Do you guys remember when we talked about horizontally projected loads? That means that this load 1 is multiplied by 18, not by the length of the beam. Okay. All right. Let's see how can we do that. Okay, but we have here different types of loads. Yeah, it's dead aligned, but they are not horizontally projected. So they are distributed over the length of the beam. So if you want to find the resultant, you want to find the length of this beam and multiply 4 by 3.5 meters. Okay, because this is 3 and this is maybe, I think it's 3 root 2. So it's a little bit over 3. Do you guys understand that? Okay, so let's do this. I'm gonna go to SAP 2000 and I'm gonna select this beam and I'm gonna go to the tab that has assign frame load. Last time we did joint load. Why? Because the loads were concentrated forces at the joints, but right now we have distributed forces over the beam. So we're gonna go to frame loads and you will find something, it's called distributed. go to distributed, and then you will find that the type of load that is predefined here is dead in the coordinate system global, and it's in the gravity direction. So let's go to the gravity, and you will find two different gravity. One is gravity and one is gravity projected. Which one I'm gonna pick? Projected, right? Well, the load is going down, but it is not distributed over the length of the beam. It's on the projected, the horizontal projection of the beam. Okay. All right. So I'm gonna say, actually, you can say also Z projected, but make sure when you put the uniform load to put it's in the negative direction, not in the positive direction. Gravity is equal to negative Z. Okay. All right. So I can make it Z projected, and I'm gonna say -1, and I'm gonna say apply. Okay. All right. I want you to check this. What happened? I applied 1 ton per meter over the horizontal projection of the beam, which is 18 meter. But when I put the load, I put 0.99. You guys understand why this happened? All right, so we assigned the load over 18 meter, but what SAP 2000 did, take the one that the 18 ton and distribute it over the length of the beam. So that's how the SAP 2000 shows the load. It doesn't show the horizontal projection. It takes the load and multiply it by 18 and divide it over the length of the beam and assign the load as over the length of the beam. So if you multiply 0.99 by the actual length of this beam, it's gonna give you 18 ton. Okay. All right. So I'm gonna do this again. I'm gonna select this beam, and I'm gonna make it gravity projected. So it's the same as Z projected, and I'm gonna change this to 1. Okay, so both are the same. And I'm gonna change the load pattern to live load. And I'm gonna say apply. Okay. So right now it's the same thing. You have this is live and this is 0.99. So right now we are done with the loads on this beam. So let's get to the load on the cantilever. We have 4 dead load and 3 live load. So I'm gonna get back here, select the cantilever. Assign, frame load, distributed, and then we can start with live. Live was 3. And I make sure it's a gravity projected. No, not projected, it's a gravity because it's distributed over the length of the beam. And I'm gonna hit apply. Let's see what's gonna happen. So you'll find a total of 3. Can see the number here. And then I'm gonna change this to 4, change this to dead, gravity, and I'm gonna say okay. All right, so it was applied. Let's make sure it was applied. I will go to display, show load assignment on frames, dead loads, and I'm gonna say okay. Oh, wasn't assigned. Okay, so let's make sure. What loads this beam have? Okay, it only have 3 and it's live load. I don't know why it wasn't assigned. Okay, assign frame load distributed for dead gravity. All right, it was assigned now. Okay, so we have the loads assigned. So what is next? I have everything done, the beam, the loads. So I believe that the frame is ready for the analysis. So I'm gonna run, but make sure to save the model. What? No, we didn't do any analysis yet. Once we run the model, so it's gonna look by itself. But what I want to say is don't wait until to come to the run phase to save your model, because if you have a really, really big model, you need to save it from VERS. That's not a big model. That's like a 5 minutes one. But if you have a building that is 50 stories, so you need to save your work every few minutes or something, every 15 minutes. But here, once you say run now, it cannot run the analysis unless you save the model. So I'm gonna, for example, save this as frame 1. And then it's going to save and then run. Okay. So let's check the bending moments. Do you guys remember if I want to show the deformed shape? This is the deformed shape due to the dead load. And if you want to see, by the way, if you want to see like, okay, let's just get up. If you want to see like 3D view of this, there's something here like this, a checkpoint. And you can go to, yeah, you can go to extrude view here. And you hit apply. So it's going to show you how is the cross section look like of this frame as a 3D. And you can show actually the deformed shape on top of this frame. And it's going to show you something, for example, something like this. How's the frame is performing, okay? That's also one way. Here you can go to the display option. You can show many things. You can show the local axes, you can show labels, the cross sections. So you can go them and check and uncheck these boxes and see how this is gonna change the view. All right. If you wanna, for example, show the bending moment, I'm gonna click here. Okay, if you wanna show the bending moment in this view, you have to click on this view. If you want to show the bending moment in this view, should be the activated view. So I'm going to show here, for example, the frames, and I'm going to choose the dead load, and I'm going to show moment M33. And I'm going to say, okay, so that's the bending moment for this frame. Okay, so here it's a negative bending moment. As you can see, that 2000 display the bending moment like the rest of the world. Negative is up and positive is down. Okay, so here, if you want to find out the bending moment at any cross section, you come here and you will find out what is the bending moment. And actually, you can right click on this beam and it's going to show you how does the bending moment look like. What is your question on this bending moment? It's linear, right? It should be a parabolic curve. But actually, the bending moment values here and here are right. But if you want to show it as a parabolic curve, the thing is, for finite element, since we draw this frame, it calculates the bending moment at the last and first and something in between. So finite elements calculate at the joints. If you want to make your moment, your analysis more accurate, you need to create more points so that the software can calculate the bending moment at. So let's try something here. If I unlock this model and I'm gonna try, for example, divide this frame. Okay, let's select them all. And I'm gonna go to edit, edit lines, and I'm gonna say divide frames. And I'm gonna go to divide it into a number of frames. Let's say we're gonna divide it into 10 pieces. I'm gonna say, okay, yeah, it's not gonna be all of them are the same size. I'm just like making an example. So let's rerun the model and see what is gonna happen. Oh, I didn't run. Run now. You see what happened? Right now, we started to have a parabolic curve and it started to calculate the bending moment at each joint that you have, and the parabola started to show up. This was actually also variable, and it started to be a parabolic curve. So that's actually something that I need to mention, that finite element method, which is this software is using. It's an approximate method. It's not the exact solution when you're solving problems. It's approximate. What does it mean by approximate? Like, for example, like if you have a slab like this and there's a column here and a column here and a column there, okay? So the thing is, solving this slab, if you solve this slab and you make it like 4 elements, and you try to get the bending moment, the software is gonna calculate the bending moment at these points and average in the middle, okay? It calculates at the points that you define. The more that you divide, the more accurate it's going to be. There is other methods outside that is our exact solution of the slab. Like there is, if you solve using the plates and shell method. I remember when I was doing my PhD, I took a class called plates and shells. This class, we were solving like a slab like this and over like 5 lectures of integrations and differentiations and a lot of stuff to solve just the slab, to get the exact solution of the slab. Because you are solving using the exact theory. And also there's another method, it's called boundary elements. This software doesn't work with boundary elements. Also provide exact solutions, like the exact solutions of the slab. It doesn't do any mesh or anything, okay? But this is acceptable. This is fast because it's all about, you need to compromise a little bit of accuracy so that you can save your time. Telling 5 lectures and we're gonna do it in 2 seconds, okay? So that's what finite element software provide to us, like fast solutions, and we can save our time and we can compromise a little bit of accuracy.
How does it translate in reality?
What was that?
How does it translate in real, application?
What do you mean? Like,
compromising a little bit of accuracy.
yeah, like let's say, for example, you are getting the bending moment here in the middle, 18.87. And if the accurate solution is 11, so we are talking about 99% accuracy. Okay, so we're not talking that this is 50% and the other is 100%. We are saying that this is 99, maybe even more exact solutions. All right, so that's for this application, and I want to do a very quick application that has triangular load because I believe this is in the homework. So let me see here. Okay, let's do this one very quick. All right, I'm gonna say File, New Model, and I'm gonna save this. All right, so I have this beam. This beam has how many spacing? Look at this. I have 1, 2, and I'm gonna make one here and one there at these dead loads because I need a joint to assign this load at. So I have 1, 2, 3, 4, 5, 6 grids in the X direction. How many in the Y direction? 1. How many in the Z direction? 1. Okay, I'm gonna make 2 so that I can show the spacing. Okay, grids is not loads, it's not anything. If you make 100, nobody's gonna tell you did something wrong. I'm gonna adjust for visualization. So I'm gonna tell you why I do this right now. So I'm gonna say grid only. And how many in X did we say? Does anybody have any short-term memory? I don't. 1, 2, 3, 4, 5, 6. Okay. 6. I'm gonna make this 1, and I'm gonna make Z2. And let's fix the spacing when we get into the view. All right, so I'm gonna make this as XZ, and here I'm gonna make a right click, edit grid data, modify, and let's see what spacing do we have here. I have 7, and 7 plus 2.7 plus 2 is 9, and another 2 is 11, and then 13, and then 15. Okay, so what I'm gonna do, I'm gonna say 7. Okay, I'm gonna add another one. It's gonna be 9. Another one. Oh, sorry. Oh, that's the Z. All right. Delete. Let's make the Z maybe 3. Add. Oh, sorry. Okay, we already have it here. 7, 9, 13, 11. Okay. Oh, it's 2, 2. Oh, yeah. 11. And then was 13 because it was another 2. And then there was 2 at the end, 15. All right, let's say okay. Another okay. And then, what is that? It doesn't. Okay, let's check again. I don't know why it doesn't take the last one. Okay, so right now it look right. Okay, and I'm not gonna define the section because that's not the, I'm gonna make the section the, you guys can define it when you do this application. So I'm gonna draw something like this, here, 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 and here. And I'm gonna look at the hinges. I have hinge to rollers. So I'm gonna choose this joint, assign, joint, restrain, and I'm gonna make hinge, apply. And I'm gonna check these 2 points. I'm gonna assign roller. And then I will say, okay. All right. So I added the boundary conditions and I'm gonna define the load. So I'm gonna define another load pattern. And I'm gonna delete the self weight and make it 0. I'm gonna make a live load pattern. Say, okay. Okay, I have loads here. I'm gonna assign load on this frame load distributed, and I have distributed load of 1 ton per meter, and it's live load. Okay, 1, and it's live load, and it's gravity, either gravity or gravity projector. It doesn't matter because it's horizontal. And I'm gonna say, okay, apply. All right. So let's get to the tricky part. All this was easy. So actually, what I'm gonna do to make it easy, and I will tell you why I did this now. I'm gonna delete this frame, and I'm gonna redraw it as a 1 frame. All right. I wanna assign load on the frame that I just drew. This one. Okay, let's look at how this load look like. It's a trapezoidal load. It starts at 0 at distance 0, and then it goes to 5 at distance 2, and it remains constant at 2, and then it goes down to 0, another 2. So to do this, we are gonna, 5. Oh, yeah, sorry, it's gonna be 5. And oh yeah, so yeah, the points load, it just goes to the 2, and then you have this. Yeah, it's a little bit tricky. So 0, and then it goes to 2.5, and after 1 meter, it's gonna be constant, and then it's gonna go to 0. Okay, so let's do this. So to do this, first, it's not uniform load, right? So I'm gonna make this 0, right? And then I'm gonna use the trapezoidal load that we have here. So it gives you 2 options. It gives you, if you want to give the loads as a relative distance or absolute distance. So for me, it's much easier to do the absolute distance because I have the absolute distance rather than taking the 2 and divide it over 5, the total length of the beam. So I'm gonna put at 0, it's gonna be 0, right? And we have 2.5, and it starts to be 5. You guys tell me because you were focusing on the lenses. So I'm gonna say not relative, I'm gonna say absolute, because if you put relative, it's not gonna be more than 1. So if I put absolute, I can put the distance by myself, 0, 0, and then 2.5, you guys have a short memory, and then 5, and then 3.5, right? And it was still 5. And then we have 2.5 on top of these. So it's gonna be 6 and became 0. And then I'm gonna hit apply. and just make sure it was live load. No, it was dead load. Okay, so I did a mistake. So how to fix this mistake? It's very easy. You are gonna change this to dead and make sure you have replace. Oh no. You should, because it's not the same. Replace existing load only happen in the same load pattern. So what I'm gonna do, I'm gonna assign this as a dead load. I'm gonna select this member and I'm gonna say apply, all right? But because I don't want to mess this numbers, I'm gonna say apply. So right now I have dead load here, and I'm gonna go back to the live load that I assigned on this member. I'm gonna say delete existing loads, okay? And then I'm gonna hit OK. All right. So I did a mistake and tried to fix it. So right now the live load is only on this member. So let's go back here. So I put the dead load. So I have 2 points concentrated load. Do you guys know right now why did I delete the 3 pieces? The member was like 3 pieces here. Because if there are 3 pieces, I will not be able to do the distances. Because everyone is going to be local at the same member. That's why I keep this member as a 1 piece and start to add the loads as a 1 piece on this member. Okay, it's gonna be, you can do it as a 3 pieces, but it's gonna be a little bit hard. You have to do the triangle burst, and then you have to do the uniform, and then you have to do another triangle. Okay. All right, so for now, if I want to assign the concentrated load, it's very easy. I don't have to delete this member. I select this member and I say edit lines, divide frames, and then I go to break at the intersection with straight frames or joints. Where's the intersection with coordinate? There is one with the grid lines. Oh, you can, this is, you can divide into a number of frames, and I know actually they are 3, but actually there should be one with the grid. Okay, selected. Last one. Oh, okay. So this is the visible grid planes. Okay, I say apply, and then I hit OK. So if you select this, should be a single. Oh, didn't. Edit line, divide frames. Oh, sorry, that's not. Okay, divide frames. All right, so yeah, so here's the thing. X, Y planes. Okay, a grid intersection. So it should be with this plane, which is Z and Y, YZ plane, X grid system. Say apply. Okay, let's check. How come? This is the X grids, right? Anyway, let's divide into frames so that we don't waste our times. Let's put 3 frames and they are equal. Let's double check. They are all 2. And then apply. Okay, so from previous versions that I used, there was something with just the grids. It doesn't matter. Okay, yeah. Okay, let's do this, and then yeah, here we have it. 3 pieces. And what I'm gonna do, I'm gonna select these 2 joints, and I'm gonna assign. Actually, there was another option that you can do. Like you can draw a joint. Like, can you see, guys? Where is it? Draw, and there's a special joint, and then you can actually draw a joint here. And once you draw the joint on the full member, you can assign load on this member. So that's also another way to do it. I believe it's much easier than the way that we are doing it right now. But anyway, all the roads take us to Rome. Okay, I have here assign joint loads, forces, and then I will go to Here I have 8 ton, they are dead load, and they are negative Z. So -8, and I'm gonna say, okay. All right, I have concentrated loads now. All right, so right now I'm done with this beam. So let's go to the next one. The next one is a triangle. So we have dead load 3 ton per meter. It's a 3 here and 0 here. So I will go back here and let's double check, is it dead or live? Okay, dead load. I'm gonna assign frame load, distributed, and okay. And then, okay, what should I do now? Actually, you can do it either way. Like you can do absolute, like I can say at 0 it was 3.
Yeah.
All right. So I'm gonna do 3. And at the distance number 2, which was 2, I'm gonna say it was 0. And these I'm gonna put zeros. And then I'm gonna say apply. Okay. So we did the triangle load. And right now everything is done, so I can run the model. Yeah, I want to teach you also how to do load combinations, so I can go to define. There's something called load combinations. And then you can add a new combo, and you can name it whatever you want, like maybe combo 1. And I'm gonna say you can add here, like I can say the dead load is gonna be multiplied by 1.2. Add, and maybe I'm gonna check the live load is gonna be multiplied by 1.6. And I'm gonna say add. So I have right now a load combination of dead load and live load. And actually, this is how we design structures. Not only for live load, but we design them for multiple loads. Just 1 second. Yeah. So I'm gonna hit OK. So I have combination 1. If you guys have the ASCE 716 for design loads for structure, you will find what load combinations that you need to design the structure for. You'll find load combination between dead live and earthquake, dead live and wind and rain and snow. Depends on what your structure is exposed to. Like here in Florida, we don't design for snow, but we design for rain. In Colorado, we design for snow. Okay, so depends on what load combinations that you need to design to. Maybe you have to define 4, maybe you have to define 5. And then once you are done, you will say okay, and then you run your model. And then I'm gonna hit run now. And then I'm gonna say beam 1 save. All right, so here, this is the bending moment due to the dead load. And it's not curved as it's supposed to be, but if you want to make it curved, you divide the beam and it's gonna look curved. And that's actually the bending moment diagram for dead load. If you want to show for other loads like live or the combination is gonna show here. And I make sure it's M33, and I'm gonna hit apply. So the bending moment should be a little bit bigger. Okay, so why there's no moment here? Let's see. Here we have dead load. Oh yeah, so there's a little moment. Yeah, something like this. Because we have a concentrated load that makes the bending moment here bigger. Okay, if you want to show the shear force, I'm gonna say apply, and this is how the shear force, and actually it makes sense. Why? Because I can see the drop in the shear here and the drop in the shear here that comes from the concentrated loads, right? So, does anybody have any questions so far on this example? All right. I believe right now we are done with the beams. I'm gonna give an introduction for the slab. I believe this is the most complicated loads that you can find. It's gonna be a little bit more complicated if you have a distributed load on top of this. Like, let's assume, let's actually come back here. Let's unlock the model. And let's display, show load assigns on the frame. And let's show the dead load. Okay. Like this beam, we divided it actually, but it's fine. So right now I have it small. If you want to retrieve the full view, you can click on this thing and you can make zoom in actually with this if you want to only focus on this part. So what I want to say is if you have distributed load on top, like the trapezoid is on top of distributed load, you can select this beam and go assign frame load distributed, and then you can add a uniform load along with the trapezoid. So anything that you are going to add here is going to be uniform, and anything that's going to add here is going to be on the top of the uniform load. So if this is 0, so all these loads are going to start from 0. If this is 5, all the loads are going to start from the 5. So let's change this maybe to make it like 2, but I'm not going to say replace existing. Because if you replace existing, so it's going to make 0 for the trapezoid. I'm going to add 2 existing loads. But if you were doing this from versed, like not starting from now, like the way that we did it from verse, I have 2, and then I put the load here, I can keep it replace existing. Okay, so let's add this on top of the existing loads. What happened?
Change the value.
Oh yeah, take the so this is because we divided the frame, right? Okay, it's gonna make it more complicated. Let's make Control Z. All right, I'm not sure. We can join the frame. Edit line. Anything has a solution. We can join this frame. Okay, it's gonna be joined like this. And let me try one more thing and see if it's gonna work or not. So assign frame load distributed, and let's say 2. But the thing, oh yeah, I see it now. I have this 3. So this is 3. It messed up with all the loads that we have because it put 3 at this location. Okay. And when we say replace, it's not only looking at what we have here, it looks at what we have overall here and here. We have some load here. All right, so let's try this one and see how it's gonna look like. All right, so right now we have 2 here, and it's supposed this is, okay, I can see it's 7. And this should be fine. Okay, so right now we know what happened. So if, for example, if you are starting from versed and you want to delete existing load, you say apply, and then you can get back to existing, put 2 uniform, and then put the loads the way that we did it. If you guys remember the distances, it was like 2.5, 3.5, 6, and then we have 5 and 5 here, right? And then we hit, what happened? Sign, frame load, distributed, 2, gravity, absolute, lie, I don't know what's going on. So yeah, it did it again. So is that difficult? So I believe having trapezoidal load and all is the most difficult thing that you can do with, but I did this because we have a homework problem. So you guys can understand how we do it. All right, so I'm gonna do an introduction to what we are gonna do next time. So next time I wanna do something like this. Yeah, this slab. So this is a system, a grid system, like a slab system, and I want to do this thing. So let's see how we can do it. All right, so I have beams B1, 25 by 70, and I'm going to assume that the slab has a thickness of 15 centimeter. What is the spacing? I believe the spacing for this was like 5 meters. So what I'm going to do, I have 3 grids in the X direction. How many in the Y direction? That's a slab system, not a truss, not a beam. So the slab system is in the XY direction, right? On here, not like the truss going up. So I have 4 grids, 3 spacing, 4 grids in the X direction and 4 grids in the Y direction. So I'm gonna go here and go to File, New Model. No. And I'm gonna say it's ton meter, grid only, 4 grids in X, 4 grids in Y. Z direction, I'm gonna make it 1. And the spacing are 5 meters in X, 5 meter in Y. Z doesn't matter. I'm gonna say okay. All right. So I'm gonna define this the beam section. So I'm gonna go to section, frame sections, and I'm gonna add new property. And I'm gonna make a concrete section, rectangle, beam 25, 70 centimeter. And I'm gonna change this to 0.7 and this to 0.5. The material is concrete. I'm gonna hit OK. So I defined the beam. So I'm gonna define the slab. That's a new thing. Define the slab. We defined before sections like frame. And right now I'm gonna define an area section because the slab is an area section. Do you guys remember the membrane and plate and shell? So we agreed that we can use membrane and plate. If it's a slab, it's gonna be plate. If it's a shear wall, it's gonna be a membrane. But we don't want to get into this confusion, and we're gonna use shell for slab and shear walls. So we are gonna only use area section. And here you are gonna find a plane and shell. There's no membrane anymore, but I believe membrane is in ETABS. But anyway, I'm gonna select, oh, there's this plane. Okay, shell, and then add new section. I believe in shell is gonna ask you what kind of shell that you want. Yeah, here you will find shell thin, shell thick, blade thin, blade thick, and membrane. So for slabs, we always take shell thin because the slab thickness is very small with respect to the other dimension. But if you have a raft foundation, because it's still like a shell section, raft foundation, sometimes it's a very thick. The thickness is like 3 meters or 2 meters. So we usually use shell thick because it takes into account the shear deformation. In slab, we ignore the shear deformation. So shell thin is good. And I'm gonna name this as a slab, for example, 20 centimeter, okay? And if I said slab 20 centimeter, it asks you about the thickness in the membrane and in the bending. So what does that mean? That means it asks you, if I have a piece of paper or something, but if the slab that way, it asks you what is the thickness that is effective in the bending and what is the thickness that is effective in the membrane, like the tension and compression. Because membrane, it has tension and compression, but the blade has bending. So we are gonna make both the same thickness, which is the 20 centimeter that we have here. So basically you put the slab thickness here and here. All right, you select the material and then I make sure it's a shell thin And that's everything that I need for now. Okay, so I define the slab thickness. And then next step is I draw because I have the beam and I have the slab. I don't need anything else for now. All right, so the beams, you can use this draw line and make sure that you have the beam activated, and you can draw them like this all at once. So I draw all the beams around the slab, and you can draw the slab system using this draw rectangular area. So there's a different ways to draw rectangular areas, like slab system. There is a one that you can pick. So if I click here in the middle, it's gonna make a slab in between the grids. Okay, or there's a one that you can draw with 2 points, and you can draw a big one. Okay, and there's one for irregular shapes. The one on the top. So this one, that means that you are gonna draw the slab point by point, like you go over them one by one. And this one, you are gonna make it like this. Okay, this one is gonna be something you pick them one by one. If you have big model, this is not gonna be effective because you will have, let's say that you have 100 grid. So I have to click 100 point. Okay, so I did the 9 ones one by one, and I made sure it was a slab 20 centimeters here. I'm gonna show you, like, if I'm gonna do them with this one. Let's delete these. And I'm gonna bake this one. All right, and then I'm gonna make one big slab like this. The thing is, the problem with this one is that I have hinges, I mean like columns in the middle, and I want to model these columns. I'm gonna neglect this shear wall. I'm gonna make it next time. I'm gonna assume that there's a column here and a column there. So I want columns all over the place here. So to do this, I need joints in the middle, and I don't have joints. You either draw joints, or actually what I would prefer is I select the beams and the slab. And then I will go to edit, and then you will find edit areas and divide area. And you go to divide with the grids. Should be here. Divide area into object with maximum size. Actually, I can do divide area into number of objects like 3 and 3, 3 by 3, but it should be a divide area based on points. Okay, yeah, intersection with visible straight grid line. Let's see if it's gonna work here or not. Okay, it worked. But also you can divide it into numbers. And then I'm gonna have hinges at all these intersections. So I'm gonna select all these hinges. And then I'm gonna go assign, joint, restrain, and I'm gonna add hinges. I'm gonna tell you next time why I put the columns as hinges. So right now, I'm done with the modeling of the slab. I just need to put the loads. We're gonna assume it's under its own weight. Okay, like I'm gonna keep the dead, define, load pattern, and I'm gonna keep the dead load multiplied by 1. That means calculate the own weight of the slab. I'm not gonna add a live load. Like we are gonna assume this is slab under its own weight. We're not here. And then I'm gonna hit run and see what is gonna happen. Definitely this is not right, but I'm gonna show you how's the analysis results gonna be look like. This is called solid slab, by the way, because it has beams and slab. So it's called solid slab if it has beam and slab. So let's see. Okay, can you see here? This is, I'm gonna show you the animation. So from what I see here, the slab doesn't move and the beam moves. Why? Because what I told you about. Because we have finite elements, calculate deflections and bending moment at the edges, at the 4 points of the corner. Okay? So you have the deflection here is 0, and here's 0, and here's 0, and here's 0. So the average of this slab is 0. So that you can see this slab has deflection everywhere, you have to divide this slab into small pieces. We have to create joints in the middle so that the software can calculate deflections and bending moments at these joints. So to do this, so what I'm gonna do, I'm gonna unlock the model, and then I'm gonna select this slab again, and I'm gonna say edit area, divide area, and I'm gonna divide this into pieces. Each piece is 0.5 by 0.5. This is number. Okay, I'm gonna divide area into objects. The maximum size of the object is 0.5 by 0.5. And then I'm gonna say okay. So we define the big slab that is 5 by 5 into small pieces. You see, that's what we call mesh. We make the slab as a mesh, and let's run the analysis and see how the deformation is gonna be look like. So right now, this slab, it takes a little bit of time because we have more joints, maybe hundreds of them. Okay, look at the deformed shape right now. It makes sense. So right now, the model is going to be a little bit heavier because we have a lot of joints to show. Interesting. It doesn't, okay, start animation. Yeah, can you guys see? Yeah, it's moving a little bit. If you want to make it a little bit fancy, we don't have time for fancy things, but just a few seconds, you can go here to show continuous contours, draw contours, and the contours are in the Z because we have the deformation in the Z. So it's gonna show you how the variation in the deformation look like. So the one that are purple, that has the bigger deformations, and the one that is in blue, it has less deformation, and you have because blue lines outside. And that's actually makes sense. Why? Because it's like the deformation is 0.55 negative multiplied by 10 to the power the negative 3. So that means the deformation are less than 1 millimeter. Okay. All right, so that's it for now. Next time, we're going to continue to build in this model, and we're going to make much more complicated slabs so that we can finish the SAP 2000. Okay, see you guys next time.